so let's start our lecture today. So we will continue the topic about the covering space. Oh, sorry, deck transformation. Yeah. Okay, so let's see. Okay, so okay, so last time okay, so remember last time we defined a map chi. Okay, so we are trying to prove part B. Okay, so let me just state that again. So the map so chi from the deck of gamma to this pi 1 of x x naught. So remember that this x is like the ambient space, and then x tilde is the covering space, and then gamma is the x tilde is the universal covering. Okay, the gamma from x tilde to x is the universal covering, and then this x is a connected locally path connected to topological space. Okay, so here this chi is given by the chi from the deck gamma to pi 1 x naught given by so we have phi goes to the gamma of alpha tilde, where this center at x naught, where this alpha tilde is an arbitrary path. In x tilde from x tilde to phi of x tilde. Sorry, x naught tilde to phi of x naught tilde. Is a well-defined group isomorphism. Okay, so group isomorphism means that it's a homomorphism, and it's kernel equal to 0, and then it's bijection. Okay, it's surjective. Okay, and then okay, so I think we just so we want to show that this is well defined. Okay, so why is well defined? Because if you have two paths, that's wait. Okay, so basically you want to show that this what do you want to show? So if you have Holy is well defined, so by phi maps to okay. Wait, Okay, so here you have the image. So you have the phi as the pre-image, right? And then the image is like this path. Okay. So basically you are saying that, okay, basically he's saying that if you have so this is a loop. Yeah, this is a loop. Okay. Wait, let me see. What do you mean by alpha one, alpha two?
Y1 equal to Y2.
Oh, okay. Oh, okay, okay. Oh, I see. Because, wait. Arbitrary path from x naught to phi x naught. Okay. Okay, so basically, okay. Yeah, I think he's saying that this if you have like two different paths, then the image is the same thing. Yeah, I think this was he's trying to say here. So therefore, yeah. Okay, so I think that shows the first result here, and then second. Okay, so hence, yeah, sorry, I didn't finish. Okay, I'll leave it. Yeah, it's like I think it's like a topological argument, right? So I think so that is if you have a symmetric space, then you have two paths that's being like composed in this direction, and then yeah, I forgot, but I think there's a standard technique to do that. Okay, I'll see if I can. Okay. Yeah, I'll leave it as an exercise for this one. Okay. And then let me think. Okay, so yeah, so this x is well defined, and then okay, so this chi is well defined. Okay, so now in general, phi one of remember we defined the phi one and phi two last time, right? So basically, yeah. So we have the two phi y1 and y2, and we fix a baseline the x naught tilde at this x tilde, right? So and then because and then we have the phi one of x tilde is y1, phi two of x tilde is y2. Okay. So then okay. So then, okay, so in general, this phi one of this alpha 2 is a, okay, so now we want to show that this is a homomorphism, okay, group homomorphism. So what we're trying to do is that, so in general, phi one of alpha tilde 2, alpha 2 tilde, okay, is a path use this x tilde from y1 to phi1 composed with phi2 of x naught tilde. Okay, so let's verify why this is a path from in x. So okay, so what is the starting point? So from in x tilde from y1 to okay. Because we know that this alpha 2 is what? We know that this alpha 2 tilde is a path. Okay. Okay, so alpha 2 tilde from, so by definition, okay, so by definition, it is from 0 to 1 to this x tilde such that it's a path, it's a new point. So we know that, so it's a path, and such that this alpha 2 of 0 is equal to this x naught tilde, right? And then the terminal point, okay, and then the terminal point, because it has some index 2, so therefore we just define it to be like a y2, okay. Okay, so yeah, because okay, so this path basically, if we evaluate at the 0, okay, so if it's 0, then it's phi1 of x naught, which is y naught, right? And then if we evaluate at 1, it will be phi 2 of x naught, right? Because this is y2. And then by definition, y2 is phi 2 of x naught, tilde, yeah. So yeah, so this is like that, okay. Okay, so I think maybe it would be better for me to show some picture here. So okay, so here let's see what do we have. So here what we have is that remember we have the x tilde, and then so how do you draw that? Let me see. Okay, so okay, let's try this graph. Okay, so we have an x tilde, and then okay, so x tilde, and then you have gamma. Okay, let's do this. Okay, so you have the x tilde here, and then x tilde here, and then you have the projection gamma, and then you have x, and then you have the gamma here, and you have x here, and then so this is like the up here is the phi 1. Okay. Okay. So what you have now, because okay, so this alpha is okay, so wait, what is x naught tilde? X naught tilde is x naught is in x. Okay. Okay. So and then what else do we have?
Yeah, so what is alpha 1? So alpha 1 is start at x naught tilde and then, okay, so we are interested in the point yj, okay. So yj by definition is alpha j of phi j of x naught, okay. Okay, so maybe let's draw the point here, okay. So this is x naught, and then this is like x naught tilde, and then under phi 1, this x naught maybe is mapped to somewhere here. Let's say that this is phi 1 of x naught, which is y1, okay. Sorry, phi 1 x naught tilde, which is y1, and then let's say that you have another point, maybe that's back to here, okay. So this is like y2, okay. Okay, so maybe this is better. So this is like a y1, y2, okay. So y1 is phi 1 of x naught tilde, y2 is phi 2 of x naught tilde. And then what is the path? So what is the gamma tilde? So it's a path with initial point. Okay, x naught. Okay. Okay, so wait. Okay. Okay. Okay, so because, okay, so here I think the graph is somehow misleading here because this, okay, because this x tilde is in F, right? And then I think this, because I think this yj they are also in F, right? Because if you map if you take the gamma, right? Because it basically you take the gammas, because we know that this phi 1 and phi 2 the direct transformation, so therefore we have the gamma composed with phi 1. Let's take phi 1 equal to gamma. So if you plug in the point x naught tilde here, it will be the same thing as gamma of x naught, which is equal to x naught. Yeah. Wait. Yes. Yeah. Okay. So then what you have is that you have that. Yeah. So this implies that this is in the in the inverse. So therefore what you have is that therefore what you have is that you have all these points that lies on the stars. Okay. So this should be the x naught tilde. Okay. So now what you do is that you draw a path, right? So this alpha 1 is a path that's start x naught tilde and at y. Okay. So alpha 1 start at x naught tilde and then and at y1. Okay. So here is like alpha tilde 1, and then so start here and end here. Okay. So maybe I add an arrow here, and then this alpha tilde 2. Okay. So here maybe let's say that. Okay. Alpha 2 tilde. Sorry. Yeah, alpha tilde 2. Okay. And then what's happened next? So okay, so now what do you want to show? So we want to show that this chi is a homeomorphism, right? So namely, okay, so and hence okay, so I think maybe it will be helpful to see phi 1 of alpha 2 what the value is. So if you apply, yeah, anyway, because it is an isomorphism, so, wait, what? Okay, so, okay, so, yeah, so let's do the, so phi 1 of alpha 2, so phi 1 of alpha 2 is a path, is in x tilde from y1 to, from y1 to, wait, y is y1. Y1. Wait. Wait, doesn't make sense. Oh, okay. Phi 2 hat. Wait. Oh, okay. I see. Yeah. Because if you take phi 1 again, right? So yeah, you imagine you are doing that direction. And then you have this x naught being mapped to, remember this x naught and this x naught, they are the same point, right? So here for this x naught, it maps by phi 1 to this y1. So here this x naught, if you consider in phi 1 of this image, then this x naught tilde will be mapped to like the y1 here, and then this y2 will be mapped to this point. Okay. All right. So yeah. So okay. And then, so hence you have this the chi of phi 1 composed with phi 2 is equal to gamma of, let me see, alpha 1 tilde composed with, or product with phi 1 of alpha 2 tilde. Center at x naught. Which is equal to alpha 1 product with alpha 2 at x naught which is equal to alpha 1 x naught. Wait. Okay. Yeah. So I think it's just the group operation, the group adding of the group product. Yeah, the operation in the parallel group. Okay. And then which is equal to chi of phi 1 times chi of phi 2. Okay, so let's see why it's true. So chi of phi 1 composed with phi 2. Okay, so what's the definition of? Oh, okay. So phi 1 composed with phi 2 of x naught is okay. So let's just go down the definition here. So by definition, okay. So chi of phi 1 composed with phi 2 is, oh, okay. So it's equal to, so okay. Okay, so you have this
gamma of let's say some alpha tilde. We will specify it later. X naught, where this alpha tilde is actually passed from in x tilde from x naught tilde to phi 1 composed with phi 2. Oh, okay. Okay. Phi 1 composed with phi 2 of x tilde, right? So since here, this one is a path from, wait, no, right? So we want to path. Oh, okay, okay. Okay. So yeah, so here, yeah, so here, I think what we just showed that is, okay, so I think if you do, okay, so I think if you do like, if you do phi 1 of this y2, I think it also lies in the stock. Okay. So let me think. Let me write. So if you compute like the gamma of this phi 1 of this y2, right? Then it's the same thing as, yeah, gamma of y2, which is because the y2, remember, y2 is in the stock, so therefore it's equal to x naught. Okay. So therefore, what you have is that, so you may have the maybe somewhere here. Okay. So this is like phi 1 of y2, which is phi 1 composed with phi 2 of this x naught tilde. Okay, so we show here that, so if this is like alpha 2, right? So, okay, so yes, this is like y1. And then maybe y2 is, I'm not sure. So forgive me, so this one looks like y2, but I label it as that. So let's say that this y2 is somewhere below here. Okay, so I use a divider. Okay, so yeah, so this alpha 2 is like that, right? So I know that from here, from this statement, we know that the phi 1 of this alpha 2 is a path from y1 to, okay, so from y1, start at y1 to here. So maybe somewhere here. So this is my, this is the path. Phi 1 of alpha 2 tilde. Okay. Okay. And then what happened next? Okay, so here we yeah. Okay, so here you think of this alpha as this one. Okay. So alpha 1 poured out with. So, okay, so what happens if I poured out with alpha 1? So what is alpha 1? So alpha 1 is from x naught tilde to y1, right? So if I copy the mirror symmetry here, well, not mirror symmetry, but exactly the same thing, okay? Right? So this is from x naught and back to here, right? So yes, so therefore this is a path, right? Yeah, this is a path. And so this is the path from where to where? Yeah, so this is the path from, because here you are starting at y1, so, and then, but, okay, you start with alpha 1, so therefore, sorry, alpha 1 tilde, okay, well, alpha tilde 1. So you're starting at alpha tilde 1, so you're starting at this x naught, and then concatenation after you end at here. Where is actually path and then end at phi. Okay, great. Okay, they are checked. Okay. Okay. And then so y
y is equal to this one. Oh, I think last time we showed this, right? So let me think. Okay, so let's see y. Okay, so I think what you have is that gamma of, so you have, okay, so here it is a gamma of concatenation of a path, right? So gamma of a concatenation of a path, so it's basically is that if you, yeah, so basically this path is like divided into two parts, right? So like one part corresponds to the image lies in this alpha tilde, and then the other part corresponds to image lies in this phi one of alpha two tilde. Okay. So now after you do the projection, then the previous part projects down to this alpha of this, because it's a continuous map, so you can just do that. And then the second part projected down to this phi one of this alpha tilde two. Okay. So sorry. Yeah. Yes, and then yeah. So and then this is definitely, yeah. Okay. So therefore we know that this one is the same as that. Yeah, and then what we have is that so we know that this one is what? We know this one is okay, we show that this one is alpha one. Okay. And then phi one of alpha two is equal to what? So phi one of alpha two is equal to okay, so phi one of alpha two is equal to what? Okay, so I want to show that this phi one of alpha two is equal to alpha two. Okay, but why? Oh, sorry, gamma of phi one of alpha two. Okay, so gamma of phi one of alpha two. Okay, so here I want to show. Okay, so y is equal to so basically the idea is that, okay, so say if you plug in the starting point, so okay, so okay, wait, no. Okay, so what's the definition of alpha tilde of alpha two? Okay. Okay, so we know that this alpha two is being defined as this gamma of this alpha two tilde, right? So therefore you know that for any let's say x here, so you put the x, so alpha two of this x, or t, okay, t from 0 to 1. And then you do a phi one, right? So phi one basically maps these two. So phi one is a, oh, okay. Because this gamma is because this phi one is a deck transformation, right? So therefore we know that because yeah, so gamma is a Dex transformation implies, oh sorry, phi 1 is a Dex transformation implies you have this gamma of this guy, okay, is equal to gamma of this guy, okay, and then by definition of this one, this is equal to gamma of what? Gamma of, wait, okay, sorry, yeah. This is, this is equal to alpha 2t, okay. Okay, since the t is arbitrary, so therefore you have the result, okay. Okay, so now let's see. Okay. Okay, I think that shows the result, right? Okay. Okay, anyway, so yeah. Wait. Why this is true? Let me think. I think this is just by the definition of group operation, right? Let me think. Yeah, so in a group, you have yeah, so in a fundamental group, basically what you have is that you have you have the oh yeah you have the product as the you have the product as the as a concatenation. So yeah, wait. In pi 1, what you have the product as? Okay, let me check. Oh, okay. Yeah, so this is by the definition of the product. Okay. And then what's happened next? Okay. Wait, okay. And then what you have is okay, so y is equal to, okay, I want to show this is equal to chi of, okay, so I want to show that, okay, so, okay, so y is equal to that because okay, so, oh yeah, this is by the, wait. So by definition, chi of phi 1 is equal to oh yeah, so remember for the definition, so this is, yeah, this is like the same thing for the alpha 1 and alpha 2, but for alpha 1 you have the initial point x naught tilde endpoint at y1, which is phi, so y1 is being defined as phi 1, yeah, phi 1 of x naught tilde, right? So here we want the, so basically here we want to, so if it's here is like a phi 1, and then you should end at the gamma of phi hat, okay, center x naught, which okay, so which this alpha tilde is an arbitrary path in x naught x tilde from x naught tilde to y1, okay, phi 1 x tilde, which is y1, okay. Yeah, so this is actually what happened here, okay. So, yeah, so you should have, okay, so why is with that? Okay, so, yeah, so this one, my definition is equal to gamma of, okay, and then because for any weight, then because yeah, so okay. So basically so basically if you take, by definition this one, if you take the projection of alpha 1 is equal to the alpha 1 is by definition the projection of this alpha 1 tilde to under the gamma. Okay. All right. So I think that completes the proof here. So oh yeah. Okay. So okay. So that shows that this chi is a homeomorphism, right? Okay. All right. So okay. So let me think. What's next? Okay, so I think I have to erase something. Okay, so maybe I'll do it here. Okay, so now, okay, so maybe I erase this one as well. So here, if alpha 1 is classical whatever is a trivial loop, then the lifting alpha 1 tilde is also a loop. By the path lifting property in 0 10.2.5 away. Yeah, so by the path lifting property. And hence, you have this phi 1 of x naught tilde, which is equal to y1, which is equal to x dot tilde. Okay, so let me see what happened here. Okay, so if alpha 1 is passed on the way to the trivial loop, then the lifting is also a loop. Okay. Okay, so let's see why the lifting is also a loop. It says by the path lifting property, right? What is the path lifting property? So the wait. Oh, okay. Wait. Okay, so we know that by definition, this alpha 1, okay, so it starts at this x naught, right? And then, y is also a loop. Okay, I want to show that this alpha, okay. Okay. By the path lifting property. Let me think. Yeah, I think what we have here is that